All right, let's get started, everybody. So we're on to 5B. We're not learning a different skill today, but we're learning an application of skills that we already have. And so what we're going to look at is if we have two functions on the Cartesian plane, let's say here's some f of x and here's some g of x, okay, then the area between those, we can find the area between these two functions, and that's going to be the integral of the top function take the bottom function. That's the technique that we're going to apply today. So we have find the area enclosed by the function f of x equals 4 and g of x equals x squared. So the first thing I'm going to do is graph both of these for you. So if here's a Cartesian plane, the equation f of x equals 4 means the y value is always 4. It's a horizontal line. It doesn't matter what the x value is, the y value is 4. That's our first function, okay? And the second function is x squared, and we're pretty familiar with that quadratic now. That's a parabola, goes through the point 0, 0. That's going to be our second function. Now we want to find the area enclosed by these two functions. So we want to find this area here. So the way we're going to do that is it's going to be the integral of the top function, okay, the one that's on top. Okay, that's what we need to graph, so we need to see which one sits above it. 4 is on top, and the one underneath it is x squared. Now, let me explain to you why this is true. If we do the integral of the function 4, we're going to find this area here. And if we do the integral of the function x squared, we're going to find this area here. And so if I do this area, take away this area, that's going to be the part that I'm left with. Okay, so it's just like composite shapes. That's why it makes sense for us. Okay, so this is the integral we're performing, but we need to go, what are the boundaries over which we're integrating? And that's just what's the lower value of x here, and what's the upper value of x here. So we're interested in a value of x. So we need to go, well, when do these functions meet? Well, one simple way to do it would be to graph both and g-solve the intersection, or we can solve it. They're going to meet when 4 is equal to x squared. When the first function is equal to the second one, that's going to be when they meet. We'll square root both sides, and we'll get x is plus or minus 2. We have two solutions, right? Here x is minus 2, and here x is positive 2. So that means we're integrating from minus 2 to positive 2. So all we're doing now is the fundamental theorem of calculus, applying that. I'll just point out one thing here as well. Because this function is symmetric about the y-axis, we could just go from 0 to 2 and double it, all right? And that's useful because when you sub-zero in, it becomes very easy to process, doesn't it? Nonetheless, let's just apply it as we've got it here. So we've got an integral statement. Let's perform the integral. The integral of 4 is 4x, and the integral of x squared is x to the 3 on top of 3. And then we've got our boundaries over which that integral is occurring. Okay, and then we're away. Numbers in. And when you get to this stage, just like in the first test, unless it says find the exact answer, we've demonstrated all of the processes we need to. We're just looking for an answer now. So you could spend a bit of time fiddling with that, going, oh yeah, that's 8 on 3. Take away, you know, there's negatives going on here. It's easy to make a mistake there. All we're going to do is put this statement in our calculator. Okay, the integral from minus 2 to 2 of 4x squared. If someone's happy, thanks, Mace, and then I'll get started on the next one for us. Actually, while we've still got this one up, can I get everyone to graph these functions, and I'll show you another integral calculus thing we can do there as well. Yep, both functions at the same time. So y1, y equals 4, y2, x squared. Excellent, thank you. 32 on top of 3. Yep. And units squared, it's an area, okay, so make sure you plug that in there. Okay, graph both at the same time. Now remember how when we go G-solve, we'll press the across arrow and there's an integral button and then it pops up with a number of options for us, okay? We're going to press the one that says intersection. So this allows us to find the area between the 2 points of intersection. All right, so that's what that one will do. Okay. All right, I'll sketch the second example up here.
It just shows you the intersection.
All right, in the second one, find the area enclosed by the y-axis, the x-axis, and the function e to the x take away 5. So let's have a sketch of this. Here's my Cartesian plane, x and y. And if we sketch the function e to the x, all right, we know that's like exponential. E to the x take away 5, it's just going to translate it down. Okay, now we want the area enclosed by e to the x, so the function, the y-axis, and the x-axis. So read it carefully, it tells you what area it wants you to find. It wants us to find this area here. Okay, it wants us to find the area from x is 0, all right, that's where the y-intercept occurs, to this point of intersection. So there's two things we need to do first here. Let's do this one exactly. Let's find out what is this point of intersection exactly. Well, this occurs when e to the x takes 5, that's the function, when the function is equal to 0. When the y value of this function, okay, this function here, when the y value of it is 0, that's when it crosses the x-axis. That's the x-intercept. Roots occur when the y value is 0. Let's solve that for x. We'll add 5 to both sides, and then ln both sides. Okay, so the exact value of this x-intercept is ln 5. So that means we're doing the integral from 0 to ln 5 of the top function take the bottom function. What is the top function? We saw before the top function was y equals 4, wasn't it? Like with this example, we had y equals 4. Yeah, who said it? Well done. Y equals 0, okay? The equation of the x-axis is y equals 0. So this means whenever you're finding area under the x-axis, the top function is 0. So I'm going to write it out. It's like the top function take away the bottom function. Okay? Now this will always end up being just the negative of the top function. The negative of the bottom function, sorry. So the negative is just, it's always 0. Well, that just disappears. It's the negative of the function, isn't it? Okay, let's process this. So I'll simplify it first by getting rid of the 0. We have negative e to the x plus 5. So when we integrate this, all right, the integral of e to the x is just e to the x. So that term is not going to change. The integral of 5 is 5x. And we're going from 0 to ln 5. Okay, we're going to find our answer exactly this time, which means we can't just plug it into our calculator and get 3 decimal places. Let's go for it. First ln 5. Okay, now this popped up a few times in the test for some people. When they had 0 as the lower boundary, they put it in and they just said that whole thing goes to 0. But you have to be careful, because when we have e, when we have some trig functions, e to the power of 0 is not 0. E to the power of 0 is 1. So we'll simplify this slowly. Now, e to the ln 5 will simplify to 5, and then we have a negative out front, so that's minus 5, plus 5 ln 5, and then this is going to be take minus 1. That's going to be plus 1. That's 0. 5 times 0 is 0. And so we'll have 5 ln 5 take away 4. Units squared. Very good. Okay. So, next one then, we have find the area enclosed by the x-axis and the function sine x over the interval 0 to 2 pi. So, if we sketch sine x, this is what it looks like. So we want to find the area of this plus the area of this. The function is sine x. So based on what you currently know, you might be tempted to just go, that's easy. We're just going to do the integral from 0 to 2 pi of sine of x. It's not quite right, all right? In fact, if you evaluate this, you will get 0. Why might that be? If we just evaluate that integral without changing it. Let's break it up into parts. If I do the integral from 0 to pi of sine x, okay, that's going to give me the area of A. But if I do the integral from pi to 2 pi of sine x, we need to do something to it first before we integrate it, because it's below the x-axis. It now has a function above it.
It's negative.
Yes, it's negative. Remember, it has to be the top function take the bottom function. Now, because in this one here we haven't treated it as a negative, it's calculated this area, and it's calculated this area, but it's calculated this area as a negative value because it's below the x-axis, and they're the same size, so when you add a plus b together, it would evaluate to 0. So whenever we have parts of functions that are below and parts that are above, we need to treat them as separate segments. So that would be incorrect. This is how we need to process it properly if we're finding the area. Another thing we could, of course, do as well is just go from 0 to pi and 2 lots of them, okay? Because that area there and that area there are the same. They're symmetrical about the norm, the line of propagation. Okay, let's do this one. So we're going from 0 to pi of sine x plus from pi to 2 pi of negative sine x, okay? Negative because over that interval, it is below the x-axis. All right, so if we go, the integral of sine x is going to be negative cos x, and we're going from 0 to pi. And then for this one over here, the integral of negative sine x is going to be positive cos x from pi to 2 pi. And then we'll just apply our fundamental theorem of calculus. Here we'll have minus cos of pi, take away minus cos of 0. Alright, so minus cos of pi, take away, so like, you know, we're subbing in the first function, take away the second boundary. Okay, so that's that one, plus, alright, so with some of this complex math, people get caught up because there's lots going on, but I think here, these skills aren't complex, it's just that there's heaps of them happening, and that's where people can get confused. We're just treating it turn by turn. We're just applying the fundamental theorem of calculus here. I have cos of 2 pi, take away cos of pi. So, minus cos of pi, we can put that either in our calculator, or you can look at the unit circle. Be familiar with it, right? Cos is the x value, pi is here, the x value here is minus 1. So we have minus 1, take away, minus, and then cos of 0 is positive 1. So that negative there, cos of 0 is 1. All right, over here, cos of 2 pi is positive 1, and cos of pi is minus 1. So collect all that, we have positive 1 plus 1, plus 1, plus 1. We've got 4. Very good. Okay, so let's rip straight into this exercise. This is going to be the base from which we can start our folio. And I probably plan on handing that out a bit later in today's lesson.